Hey guys, today we're doing Chapter 3, Section 1, which is on changing windows. So the first thing I want you to do is use your graphing calculator to graph y equals x squared on the following windows and sketch them on the grid below. So if we want to graph y equals x squared on our graphing calculator, and I want a window from -10 to 10 and -10 to 10 for my y's. I'm going to go into my graphing calculator and I'm going to hit the y equals button and I'm going to type in x squared. Okay, then I'm going to hit the window button, and this is where you can go and change the window to whatever you want. So notice that it said for my x values I'm going from -10 to 10. So my x min I'm going to go -10, my x max I'll go to 10. And then down here for my y min I'm going to put -10 because my y values were going from -10 to 10 as well. So my y max is also 10. Okay, then I can hit the graph button right here. And this gives me what my graph is going to look like. So now I'm going to go back to my notes, and I'm just going to kind of sketch in that graph. Looks something like this. Okay, now I'm going to do the same thing over here. So I've already graphed my function, but now I want to change it so that my window goes from -10 to 0 and -10 to 10. So if I go back here and I change my window to go from -10 to 0, and I hit the graph button, now my function looks like this. So I'm going to go back to my notes and I'm just going to kind of sketch that. It looks something like that. And then my last one here, I want to go from -10 to 10 for my x values and 0 to 10 for my y values. So when I graph that, it looks something like this. Okay, so now I'm going to go back to my notes and sketch that out. Okay, so now that we have all these three graphs, this is the same function sketched on different windows. What you should notice is that they look kind of different. So windows are actually really important because we need an appropriate window in order to show the important points of our function. So I know that y equals x squared, that's a quadratic function that should look like a parabola. So right away when I look at these three graphs here, I notice that this graph is not a good graph because it doesn't really show me that it's a parabola. When I'm looking at this, if I didn't know anything else about this function, I might say, I don't know, maybe that's exponential. I don't really know what type of function that could be. Okay? When I look over here, I can at least tell that this is a quadratic function. But this also isn't really the best graph because there's a lot of empty space here that I don't really care about. So this window here would probably be the best window for this function, just because not only does it show the shape of the function, the fact that it's a parabola, but it also doesn't really have a lot of that dead space. So when you're thinking about a window, first thing you want to think about is this going to show what type of function I actually have? Okay, is it going to show all of my important points, such as like for a quadratic, for example, the vertex is really important, the maximum or minimum, which is also the vertex. It's also important to kind of see which direction it's facing, maybe if there's any x-intercepts or y-intercepts, you want to see those things. And then you also want to think about, can I change my window so that I'm getting rid of any dead space? Okay, parent functions are the simplest form of an equation for a certain type of function. On page 162 of your textbook, you'll see a whole bunch of parent functions listed out, and honestly, I would just memorize those because it's really important to know the general basic idea behind different types of functions. So when I say the simplest form of an equation, I mean literally just the simplest form. You're not adding, subtracting, multiplying, dividing anything. You're not taking anything to any unnecessary powers. You don't have any really parentheses anywhere. Okay, nothing extra. So a linear parent function is just y equals x. Okay, because that would be the most basic linear function you could get. Okay, a cubic parent function, y equals x cubed. A hyperbolic parent function is y equals 1 over x. So it's basically just the most basic form of that type of function. To find the parent function from a given function, all you have to do is remove the coefficient of x and remove all additions and subtractions. So basically you're just getting rid of all the extra stuff, and that gives you the parent function. So for these 3 or 4 examples here, we want to write the equation for the parent function of the given function. So looking at this function here, I've got y equals the square root of x minus 3. So notice that I'm going to remove the coefficient, I'm going to remove all additions and subtractions. So if I get rid of the additions and subtractions here, I don't have a coefficient, but I get rid of this negative 3, I just get y equals the square root of x. So that's my parent function. Okay, in this next one, you'll notice this is a step function. So this is my rounding down function. If I get rid of the coefficient of 2 and the subtraction of 4, I'm just left with y equals the rounding down function of x. This one here, I don't have a coefficient, but I do have this negative 5, so if I get rid of that, I just get y equals x squared. And this one over here, I don't have a coefficient. I do have this minus 4, and then this 3 on top, well, that is in my my numerator, but I don't want any numbers that aren't really necessary, so I'm just going to change that to a 1. I can't change that to an x or anything because there's no x there, and I can't move this x squared anywhere because it's in my denominator. If I move it up to my numerator or just move it somewhere else, that's not going to be the same type of function. So this would just be y equals 1 over x squared, which is your inverse square function. So these are just some types of parent functions that you have. Remember that an asymptote, I know we've talked about this a lot in this class, we're going to continue to talk about it. An asymptote is a line that the graph of a function approaches as the variable x approaches some fixed value, or as x increases or decreases without bound. So in other words, if you're graphing your function, let's just say I'm graphing y equals the square root of x. Okay, if I graph that function, that's going to look something like this. Okay? This function actually does not have an asymptote because it stops right here. It doesn't actually continue on and approach anything. And this just increases without bound. It's never going to approach a number. It's just going to keep going. Okay, this function, your rounding down function, remember that's your step function, so it looks something like this. Okay, something like that. So when you have the rounding down function, this also doesn't have an asymptote. It has points of discontinuity, but it doesn't have an asymptote because there's never a point where it's just approaching a value infinitely, but it doesn't reach it. Okay, this one, your parabola, that also doesn't have an asymptote because these can just keep increasing either direction. Okay, but your inverse square function, this one looks something like this. Okay, this actually has 2 different asymptotes. This has an asymptote at the x-axis because each of these are going towards the x-axis, but they're never going to reach them. And then it also has one at the y-axis because each of these are going towards the y-axis, but they're never going to reach one. So this has asymptotes at y equals 0 and x equals 0. You might want to go through the parent functions on, what page was it? Page 162. I would go through each of those parent functions and just make sure that you can list out the asymptotes for each of those parent functions and just determine whether or not something has an asymptote. Okay, points of discontinuity arise when the graph of a function appears to jump. These occur at asymptotes and in step functions. So remember that points of discontinuity are points where if you are trying to graph it, you have to lift your pencil up off the paper. Okay, so again, looking through these graphs, this graph does not have any points of discontinuity because when I graphed it, I didn't have to lift my pencil up. This one does, but it doesn't have any asymptotes. This one has no points of discontinuity at all. And this one has points of discontinuity at the asymptotes. Okay, so like right here, that would be a point of discontinuity because when I'm trying to graph it, I lift up my pencil off the paper. Okay? All right, and that is everything for section 1.